So folks, our trip to the lab yesterday was so you could make a pH curve, or so you could see the data that would be used to make a pH curve. Now, hopefully, people collected data that looks the way I'm going to show you in this lesson, but if you didn't, this is what it should have looked like, okay? Now, yesterday, the first thing I showed you was what it looks like when you titrate a strong base with a strong acid. Even though we didn't test this in the lab, it was the example that I showed you. We're just going to be a little bit more specific about what happens. So, ideally, you've already drawn this graph. You drew it on your lab handout yesterday. You can certainly draw it again here. I'm going to have 1, 2, 3, 4 different pH curves to show you. So if it was me, I might just draw one big graph and have different colored lines for the different curves, whatever you want to represent. Now the thing that's different here is that we're not just going to make a graph, but we're going to explain why the graph looks the way that it does. So I'm going to draw the pH curve, but then I'm going to explain what's happening on each part of the curve. So as you're writing stuff in your handout, just keep that in mind. There's going to be some explanation that goes with it. So yesterday, I showed you that when you have a strong base and a strong acid, you should have a pH curve that looks more or less like this. A flat region at the beginning, a sharp change, and a flat region at the end. I'm going to guess that your pH curves from your lab data would look somewhat like this. Quite a few of you said, holy cow, my pH did nothing, 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 and then it changed by like 4 points in one set of 2 milliliters. There was a drastic change. Now, if we take a look at what's happening at the beginning of this titration, first of all, how did I know that the pH started high and went low? Well, I'm titrating with an acid, which means it is the titrant. The volume along the bottom is always the volume of titrant that has been added. Sometimes a diploma question literally is asking you, if this is the shape of the pH curve, what was the titrant and what was the sample? And you have to get that I started out with a base and that I was adding an acid to it. Now, why is this initial pH very high? Well, it's because there are way more hydroxide ions than hydronium. Remember that even in a really strong base, I wouldn't ever say that there are 0 hydronium ions. I would always say that the concentration is really, really low. Water always makes both ions. That's why there's the water ionization constant, that Kw. If we look at the final pH, it's low because there are way more hydronium ions than hydroxide ions. So if we were looking for the explanation for why it's high and low, it always has to do with the relative amount of hydroxide and hydronium, because that's how you determine pH and pOH values. Now, what's happening in this section right here? So for this first little section down here, you all noticed this in the lab yesterday. You were adding 2 milliliters at a time and nothing was happening, or it was changing very little. Does anyone understand or maybe want to take a guess at why the pH didn't change very much at the beginning? So I was adding hydronium ions. Why didn't the pH start decreasing? Yeah. We are increasing the volume by a little bit, but that isn't going to be the main reason that it's not decreasing. They're neutralizing each other. In the beginning, there's so much hydroxide that the little bit of hydronium that I add gets neutralized right away. So, as hydronium is added, it's neutralized. So for a while, because I'm adding a little bit at a time, there's such a huge excess of hydroxide ions that those ions will easily neutralize the hydronium I add. You might notice the pH changed a little bit, not a ton, recognizing that a few of those hydroxide ions are going towards neutralizing the acid. Now this section in the middle, this drastic change, you want to look for on a pH curve because it's going to give you a lot of information. When you are trying to figure out where the titration ended, you want to look for the point that is in the middle of the drastic change. So that's where you have to use your powers of estimation and decide approximately where the middle is. Sometimes it'll be really obvious, and sometimes you got to judge, but you're looking for about the middle of the drastic change. In this scenario, the middle of the drastic change should have been where the pH was 7. Because I had a strong base reacting with a strong acid. Now this point, where the pH is 7, we call this the end point. Now why would we call this the end point? Well, this would be the point where we have completely reacted all of the sample that we had with titrant. When I go past the end point, now I'm adding more titrant than I needed. I didn't need that much for the reaction to complete, but I kept adding more. If I imagine that there's a dotted line to this point on the x-axis, the same point that will give me the end point pH will give me the equivalence point for volume. Now notice they're both referring to the same spot on the pH curve, but one of them is addressing the y-axis, the pH, the other one, the x-axis, the volume. So the middle of the drastic change on a pH curve will tell you the endpoint pH and the equivalence point. The equivalence point, this is when moles of acid are equal to moles of base. And I said in our review today, we were going to start talking about acid-base stoichiometry. Here it is. We know we're at the end of a titration when we have the same number of moles of acid and base reacting. That's when the reaction was complete. Now, when we see a drastic change, it tells us that there was a proton or H+ transfer. Now, a lot of the time, there'll just be one proton that's transferred. But I know a few of you asked, well, what would be the scenario if the acid had 2 hydrogens? Well, we'll continue with this topic tomorrow, but you might get 2 sharp changes in your pH curve instead of just 1. Now, the last piece of info is how to pick an indicator. Does anyone remember how to pick an indicator? Maybe you remember doing this in Chem 20. So if this is my reaction, how should I pick an indicator? So it has to do with that endpoint pH. This endpoint should be in the indicator range. Now, what does that mean? Well, it means that I should pick an indicator where the low end of its range is less than 7 and the high end of its range is more than 7, where 7 is in between. So if you look at the indicator list in your data booklet, I wouldn't want to pick, for example, methyl red. Methyl red has a low end of 4.8 and a high end of 6. 7 is not in between those values. But bromothymol blue, the one that we used in our titration yesterday, has a low end of 6 and a high end of 7.6. 7 is in between those values, meaning this indicator will change color as we go past the endpoint. That is how you pick an indicator. A lot of the time, picking an indicator is the question that you have to answer about a pH curve. You have to look at the curve, determine where the middle of the drastic change is, what pH you're at, and which indicator might be useful. Does anyone want to ask anything about that? Now, there was lots of detail in this explanation, so that as we go through the others, I can go more quickly because it's the same ideas, but sometimes in different directions. Now, if we did an example very specifically with data of a strong acid with a strong base, I could put 25 milliliters here on my graph. And when I draw my sharp change, there's the middle of it right about there, that middle point of the sharp change of my pH curve should be at 25 milliliters and pH 7. Now, why should it be that way? Well, let's think about it. This is a volume, this is a concentration, this is a concentration. I said that the equivalence point, so that number of milliliters on that bottom axis, would be when you have the same number of moles of acid and base. So I would figure out how many moles of acid did I have and how many moles of base did I need. Oh, I just realized I drew this upside down. Everyone else notice that? Good. I drew it upside down. It should be going from small to high. So all that talk of babies before really threw my game this afternoon. Now, if you want to figure out how many moles you have of something, concentration times volume. Now here, these are milliliters. This is moles per liter. So just be cautious when you're calculating things that you have the correct units. Since the concentration of the acid and the base are the same in this question, I don't actually need to calculate since the concentration is the same. If I want to have the same number of moles, I need the same number of milliliters. Now, it won't always be this way. In fact, I would be willing to say it wouldn't be this way on a test question. So you would calculate how many moles you had of acid by multiplying concentration and volume. Then you would say, well, what volume would I need to have so that I can have the same concentration and the same number of moles as before? And in this case, it will tell me 25 milliliters. And that's where the middle of the sharp drastic change should be. Now, this is a strong acid with a strong base, or a strong base titrated with a strong acid. Either way, the endpoint should be 7. if we have a different scenario, in this case, weak acid with strong base, things will look a little bit different. Let's put pH 7 right about here. Now I'm going to titrate this, and like it said, weak acid. And I'm going to titrate it with NaOH. So NaOH is my titrant. So I'm starting out with something that's a weak acid. Do you think a weak acid has as low of a pH as a strong acid? No, it doesn't. That was one of our descriptions of a weak acid. The pH isn't as low. So I might start my line a little bit higher than I would have otherwise. When I draw my pH curve, notice how it wasn't as flat at the beginning? That was on purpose. That's not just my poor drawing skills. But it wasn't as flat at the beginning because that was a weak acid. It's not going to do as good of a job of neutralizing a really strong base as a strong acid would. Now, if I look at the sharp change in pH, let's estimate the middle right about here. It's not at 7. And that, again, is not a mistake. Now, what is the pH exactly? Well, that's going to depend on which acid, which base, what concentration. But the idea that you should recognize is that, gosh, what is my issue today with the symbol? Let's try again. It's greater than 7. How much greater? Greater. There's a way to calculate it, and if you are super keen on doing that, continue to take chemistry in university, or you can ask me and I'll show you. But it's beyond the scope of what we expect you to be able to do in this course. So the end point of this titration should be greater than 7. Now, if you look at what we were using, we had a weak acid and a strong base. The base was stronger than the acid. The pH is higher because the base was stronger. So if I think about what's happening in this scenario, and I look down here at the volume of NaOH that I would have to add, I would still calculate the equivalence point the same way, because I'm going to calculate moles the same way. Concentration times volume is how I calculate moles. So I would expect this to be 25 milliliters. They had the same concentration. Now here's what would be different in my explanation. Like I said before, the beginning of the pH curve wasn't as flat. The concentration of hydronium was bigger than the concentration of hydroxide, but not by as much, right? The pH wasn't quite as low. And because there wasn't this really big difference between their concentration, not like if I had a strong acid, it wasn't as probable that as I added hydroxide, it would get neutralized by hydronium because there was less hydronium to neutralize it. Now, if I think about what's happening at the end point, when I have a strong acid and a strong base, they completely react. I should get water as my product because hydronium reacting with hydroxide gives water. But if I consider what's happening here at my endpoint, because I had a weak acid to start with, I should have its conjugate weak base still present. So At the end point, instead of being completely neutralized and having just water, or having a neutral ionic solution, I have a weak conjugate base and I have water. So there's a base present. The pH is higher than 7. And as I get up here to the end, now the concentration of hydroxide is way more than the concentration of hydronium. And if I had to determine what was the pH of that NaOH that I was adding, the pH that I am at the end of my pH curve should be pretty representative of the NaOH all by itself, because at this point, I've totally neutralized all of the acid, and now I'm just adding base. Now, if I said that this pH right here was 11, could someone tell me an indicator that would be a good choice to use? So you want an indicator where 11 is bigger than the low end, but smaller than the high end. So if you look at the two numbers, 11 should be between them. You want to give it a try? Yes, the weird yellow, alizarin yellow, I think would be a great choice here, because 11 falls in between the two numbers given for its pH range. I heard a few people start out by maybe saying phenolphthalein, but phenolphthalein's range isn't high enough. It doesn't go past 11, and so even though it would change color over the course of this titration, the endpoint isn't in between the two numbers in its range. Now, if we consider the last example, in this one, we are going to have a weak base reacting with a strong acid. So the titrant that we're adding is our HCl. Now you'll notice I stuck with the same concentrations and volumes on this so that you could see that we're just looking at numbers of moles here. Now because we're talking about OCl negative, which is a weak base. Now how did I know that was a weak base? Well, I wrote it on my paper, but also in my data booklet, I would look and I would see, oh, I remember the rule. In my data booklet, only the gray line or below is a strong base. Really, only hydroxide is strong. For acids, only the gray line or higher are strong acids. So I know that OCl negative is a weak base. So we'll start the curve kind of the same way we started the last one. It's not super flat. It's kind of starting on a downward slant. And when I make the sharp change in pH, and I look where about is the middle of the drastic change in pH, here's 7, and my endpoint is something that is less than 7. What exactly is it? We could calculate it, but what's more important is that you recognize it should be less than 7. So that is your marker. Should the endpoint be 7? Do I have a strong acid and a strong base? Should it be more than 7 because I had a strong base but a weak acid? Or should it be less than 7 because I had a strong acid with a weak base? If I think about what's happening at the end point here, I have water now the water I got, because the strong acid, when it reacts, should end up making a molecule of water. But I should also have the weak conjugate acid. Strong acids react 100%, but weak bases don't. They would be in equilibrium. Only some of the weak base would react, and I would be left with weak base and its weak conjugate acid. So the rule is if you have something that's weak, its weak conjugate will be present at the endpoint. If you have something that's strong, it should be making water at the endpoint. Now if I take a look in this particular scenario, let's say that the pH is 4 right here. Could somebody pick an indicator that would be good for this endpoint? Methyl orange. So methyl orange, if you look at its numbers, go from 3.2 to 4.4, so it'd be a good choice. Anybody else got one that they want to pick? Brome cresol green would work because it goes from 3.8 to 5.4. Now, I'm just going to maybe point something out. Maybe some of you might think, oh, cresol red, because between 1 and 7, there are 2 different numbers. But if you notice, it's a really big range. And even though, yes, technically, 4 falls in between that really huge range for cresol red or, say, thymol blue, it's a really big range. I would pick an indicator that had a smaller range over one that had a really massive one, especially if 4 was the pH I was looking for. Now, thymol blue might be really useful if you're trying to detect something that's just above 8 or that's between 1 and 2. But if you're trying to detect something in between those 2 ranges, it's probably better to choose a different indicator. Now, this is the end point. This is the equivalence point. Can someone tell me how many milliliters should be written down at the bottom when I'm at my equivalence point? 25, because it's the same numbers as all the other questions. But more importantly, because we are calculating when do we have the same number of moles of acid and base. Now, does anyone want to ask any questions there? Now, the reason that I don't mind starting this lesson right away is because it's really the same topic. We're just adding a little bit to it. Some pH curves have 2 or maybe more rapid changes in pH. When you did the second titration, the one with the sodium carbonate, if you graphed your data, chances are you saw the pH change once and then maybe level off and then change again. That's what should have happened. The idea is that 2 or perhaps more quantitative proton transfer reactions happen. Remember, every time there's a sharp change in pH, it means that a proton was transferred. So if we consider the first example, we're titrating carbonate ions with HCl. That's exactly what we did in our lab. So this is hopefully what your pH curve looks like. We start with a pretty high pH. Then it decreases. Then it decreases again. Now, if I look at this pH curve, I'm saying that there were 2 distinct endpoints. An endpoint is the middle of the sharp change in pH. So if I look, I put a dot on each of my endpoints. Now the line that I drew over to the y-axis is just there so I can see things. Now without calculating things, I could probably predict where these endpoints are. When I started out, I had a weak base. And I progressively added acid until 2 proton transfers happened. Now, a lot of the time, what you'll have to do isn't predict the pH, but rather read the pH off of a graph. So be able to determine by looking at a graph where the endpoint is. Now, when I'm looking at the sharp change in pH, I'm saying that about that is the sharp change. See how I was ignoring the first little section where it was changing but very slowly? I waited until the change was drastic before I tried to estimate the middle of the sharp change. Same thing right here. That's about the section where I was estimating there was a sharp change in pH. Typically, if it's an exam question where you have to determine the endpoint, the answers are so far apart that even if you estimated a little bit differently, higher or lower, you would still get the correct answer. Or they make the flat section so flat that you can't mistake where the sharp change starts. Now, if I consider what happened, because that's what we're going to focus on here, I started out with my weak base carbonate. The sharp change in the pH curve means a proton transfer happened. Bases are proton acceptors. So that means in this first portion, carbonate ions became bicarbonate ions. So because a proton transfer happened, the acid that I was adding as my titrant donated a proton to my base. Now, in the second part of the reaction, carbonate ions aren't my reactant anymore. They're part of the first reaction, but the second reaction is where now this substance, which is amphiprotic, do you notice? It could be an acid or it could be a base. In this scenario, it's going to be a base. It's going to accept another proton, making H2CO3 at the end. Now that's what's going on with my base. Since in this question I had a strong acid, at the beginning, I would be reacting that carbonate ion with hydronium. Because hydronium will donate a hydrogen, water should be the other product. Just like if I had one curve with a sharp change, I had a weak base reacting with a strong acid. So after the proton transfer happened, I had the weak conjugate acid and water. Now, because water is not what I'm adding titrant, I continue adding hydronium here. It's going to donate its hydrogen to bicarbonate, and I'll end up with more water at the end. So if I had to use some vocabulary words to describe these substances, I would call hydronium monoprotic. Mono means one. Things that are monoprotic can accept or donate one hydrogen. CO3 negative is a weak base that will eventually react to accept hydrogen ions twice. We would call this polyprotic. Poly means many. In this scenario, it means anything more than one. But it's polyprotic because it could accept not one hydrogen, but two. One in the first step, and then another one in the second step. Now, sometimes instead of polyprotic, we could be specific and say diprotic, because 2 was specifically the number of hydrogens it was going to accept. And you can usually tell that something is going to be polyprotic when it's a base by looking at its charge. Things that have negative charges greater than 1, so like -2, -3, should be able to accept more than one hydrogen ion, so we would call them polyprotic. Now, I said that hydronium was monoprotic. For the acid to be polyprotic, there would need to be more than one hydrogen that could be donated, and hydronium is just going to donate one hydrogen. We have phosphoric acid being titrated with sodium hydroxide. The word with tells me that sodium hydroxide is what I'm adding. Now, if you write down the formula for phosphoric acid, H3PO4, you might look at it and say, huh, there's 3 hydrogens there. How come there's only 2 endpoints? In a lot of cases, the number of hydrogens tell you how many endpoints there could be. But we all know that in real life, sometimes things are so slow or too weak or they don't happen. That's the case here. Even though there's a 3 in the formula, there's only 2 endpoints because the third reaction is too weak and won't actually happen. But in this scenario, we would have a pH curve that goes up something like that. Now, if we consider what's happening in the first section, I'm starting with hydroxide ions, right, because I have a strong base, and H3PO4. H3PO4 is going to donate a hydrogen. I'm not going to replace this with hydronium because it's not a strong acid. In the last one, I replaced HCl with H3O because it was a strong acid. That means that when I get to this point, I have a molecule of water and H2PO4 negative. Now, because I continue to add titrant, I add hydroxide here, and I can show the second reaction where H2PO4 negative is going to donate a hydrogen to hydroxide, leaving me with water and HPO4, H2PO4, 1 negative. H2PO4. No, I was right the first time. HPO4, 2 negative. Let's just rewrite it. Now, technically, if you look at HPO4, 2 negative, it has a hydrogen. And you might think, well, it has a hydrogen, should be able to donate that hydrogen. But because the question told you there were 2 endpoints, it's telling you that that third reaction isn't going to happen. There's not enough strength in that acid left to have a quantitative proton transfer. So even though you could maybe have seen 3 endpoints, you're only seeing 2. Now, does anyone want to ask anything here? Most of the time when we're talking about pH curves, you have to do things like identify whether the acid was polyprotic or not, or whether the base was polyprotic or not. If I looked at this pH curve and I didn't tell you what the substances were, it is not obvious whether the acid or the base was the one that was polyprotic. Typically, the sample is the polyprotic thing, but it doesn't have to be that way. but typically that's the way the curve would work. Now I think we'll finish the other part of this